Okay, sorry about that. So hi, my name is Skylar. So I'm a developer of a new hardware description language called Chisel, and also related to a thing called FIRRTL. But what I'm going to be talking about today is about how to build accelerators for the accelerator socket that Luca was just talking about for ESP. But about trying to use like all the power of like software engineering to make it like dead simple for people to build accelerators. Okay, so this is sort of like a classic like academic slide that's basically just saying that accelerators are important because we're in this sort of end of Moore's law era. And so one thing you can always do to get a lot more performance is go and build accelerators. However, with sort of one caveat from like a pretty cool paper that was just saying that the big benefits you get from accelerators are sort of one time. It's not about like iterating on the, oh right, we got Dave Wenslaff in the room. So basically just saying that like, hey, if you want to build an accelerator, you're probably going to get a big benefit going from CPU to accelerator. Thanks, Palmer. But after that, so basically just the design is important. You want to make it easy for people to build accelerators and do it fast. Okay, so but usually I like to think about things in terms of like type hierarchies. So really what we're concerned with at this point are loosely coupled accelerators as opposed to tightly coupled accelerators. So something like SIMD instructions you might add to a processor. This is like something that's like a fixed function accelerator, something that you would think about. You have a C function. You want to go and build an accelerator that's then going to go and accelerate that C function. So in this case, things like a fast Fourier transform, or the model that you would have for something like a GPU, where you do like a CUDA mem copy over to the a GPU. You then go and run some kernel on it, and then you do a CUDA mem copy back, or stuff like a neural network. I have a neural network, and I have an image, and I want to classify it or something like that. So this is sort of the restricting the domain of the problem that then we're talking about here. And just to sort of concretize that, this is sort of just like an example, like toy timing diagram of an accelerator that is just doing computing the sum of all the memory, or computing the sum of an array in memory. And what that looks like is you start off at the top and there's some configuration. You're saying, hey man, go look at address hex 0 or hex A. It's a vector of size 3. And I want you to compute the sum and write the output to address B. So that happens. The accelerator says, OK, I'm working. It goes off and does a DMA request onto address A, goes and grabs that data. The data comes back over multiple cycles. Here you're seeing that with 1, 2, 3. The accelerator does some computation. OK, computing a sum is not that complex, but it finishes sometime later. The result is 6. It writes it back, and then it reports that it's done. So these are like the sort of the class of accelerators that I'm talking about for this. All right, and this example of sort of building up an adder accelerator is sort of goes through this whole talk, and there's also an example available on the GitHub right now. Okay, so Luca's embedded scalable platform comes into the picture here because it's basically saying we want to be a platform where you can go and just grab your accelerator. You have an accelerator, you want to build an accelerator and just integrate it with the system. And sort of the pitch for that is great. Bring your accelerator in any language. The accelerator can then be easily integrated with this SoC. But there's sort of a couple of little flies in the ointment here if you want to go and build in like Verilog or VHDL. So, and the first thing is the ESP framework has to know about the accelerator. So in the sense, there's all this metadata that you have to describe to that nice, pretty GUI that Luca was showing, and that's all in the sense of an XML file. The second thing is there's sort of a defined interface for this ESP accelerator, but you can also configure that with additional configuration lines if your function has more parameters, right? Now, the thing that's annoying is if you go and just, put this in a README and just say, okay, you have to write this file, maybe you provide a schema for it, and you also say, I have these wires and they have these names and you have to code to that. That's really brittle. You're basically saying that a user has to go and parse a spec and come up with a bunch of correct strings that are going to work with the system. And I sort of come from the school of, I would like to just provide something that is, I would like to get a compiler warning if I screw up any of this. So for that, and just as one more example just of what this accelerator kind of looks like, you have an ESP accelerator here. The things which are in green or sort of a white color are things which are fixed. So the socket is providing a DMA port, a debug port for like an error code if when you're done, something the accelerator can say it's done, and something that the processor can then say, for the accelerator to start working. But everything in red is something that the user has to go and implement. And these are things like you have an optional vector of configuration parameters that you can that you have to pass to this. You have all of the business logic associated with the internals of the accelerator, and then you also have this XML, which is supposed to be consistent with what you've written here. Okay, so the usual answer for something like this is, well, just code it up in, Verilog, System Verilog, or VHDL. However, Verilog and VHDL are kind of annoying because you don't have optional I/O. This is just like a fundamental feature that they don't support. Second, we're kind of coding in the 1970s here, or even worse, even earlier, but there's no object-oriented programming in Verilog, System Verilog, or VHDL. With the slight caveat that System Verilog supports classes, but only for verification. You can't go and build hardware that uses any of this stuff. And with the slight caveat that even with the base jump STL stuff, great work for Michael Taylor, but he's even highlighted System Verilog has some annoying features that make it hard to try and do this kind of stuff. So where then I come in is with a language sort of jointly developed at IBM, UC Berkeley, and a startup, well, a not so small startup called Sci5, called Chisel and FIRRTL. What is Chisel? So Chisel is a hardware domain-specific language. So think of it's like you have a bunch of classes that are describing hardware components, and then you can go and extend them and add things to them. And FIRRTL is a circuit IR. So you guys all know about LLVM IR. This is basically just LLVM IR is program IR. FIRRTL IR is for describing hardware circuits. And you put all this together, and the benefits of the fact that this is a language in Scala is you get all the benefits that Scala has to offer. So you get simple parameterization, you get parametric polymorphism, you get first-class function support, functional programming, and object-oriented programming. So basically, you don't have to wait for the vendor tools to come along and say, well, or you don't have to wait for a standards body to come and build out, to come and make an addition to the System Verilog specification. You can just say, hey, I'm going to go and use all of this awesome power to go and build hardware. All right, so what does this process then actually look like? You write your circuit in Chisel. That runs through the Chisel front end. That generates FIRRTL IR. That runs through the FIRRTL compiler. That generates a lowered form of FIRRTL IR, and then that runs through a Verilog backend, and you get Verilog out of it. You can customize this whole process with custom transforms that you inject into really any stage of this process, but here it's just shown in adding custom transforms into the FIRRTL compiler. Okay, so there's a whole website on this, chiseleng.org. It's an open source project. Check it out. But what the point of this talk is how you can try and use Chisel to restrict and define sort of like a hardware API for this ESP accelerator socket. So the sort of abstraction that we came up with is this notion of a specification and an implementation. So a specification is sort of the encapsulation of one of these sockets, and then the implementation is the actual hardware associated with that. So for one specification, you can think about lots of different implementations. Like, as an example, you could build an FFT accelerator. It could either be pipelined or not pipelined. Those would be two different concrete implementations, but they would all have the same specification. So the specification is the thing that handles all of the configuration. What are my IOs? How much memory do I need? All of those types of things, but the implementation is the actual hardware. So for this, then, and this is also sort of a type hierarchy kind of thing, from the Chisel 3 module class, which is just a generic hardware module, you have an ESP implementation that extends that, and an accelerator mixes in a specification with that. Okay, and so I think this is on later too, but this is the website of the project for this specific part of it. And then sort of going off of this example adder accelerator that we have from before. So this is sort of what the code for writing the specification for this adder is. So you have 3 parameters here. So these are the things that you would configure. You have your read address, your size, and your write address. Some additional things that are useful for humans to look at, like a name or a description, as well as things that the ESP framework cares about, like what is the memory footprint, as well as device ID. So what's cool is that I can just say, hey, you as a user, if you want to go and work with ESP and write Chisel, you just have to implement this API. this is, I mean, it's just an abstract class. If you don't implement it, the compiler yells at you, or if you miss something, it'll yell at you, and that's nice. You want errors as early as you can get them. All right. So then the implementation is really just something that's mixing in that spec. You define the actual implementation name. So how do I differentiate this from other implementations? And then finally, like all of the business logic associated with this. So if you want to look at this example, I finished it. It's up online last night. You just go and look at it, check it out. Okay, so sort of the quick like kind of can demo for what's going on here. You just go into the project, you type spt run. This will go and build all of these accelerators for you. One of them is this sort of toy adder accelerator. But what you get out of that is just automatically you wind up with Verilog for this accelerator, and you also get this XML file. And what's really going on here is that we add a transform into the FIRRTL compiler that goes and looks at the design and then emits this additional XML data which we care about. And then these are the two things that the ESP framework wants to consume, and then you're ready to go. So basically, there's no confusion on what is this supposed to look like, what is the interface, what is the schema for the XML. We just take care of it for you. And I think just give you some concrete idea of what that XML output looks like. This is what it expects. You know, what are the configuration, the optional I/O that I have for my design, and there. And you can see this example online. And then sort of finally just wrapping all of this up. So we currently have like 3 ESP Chisel accelerators. 2 of them are toys, 1 of them is not. There's a counter accelerator, which is just like, report done after n cycles. There's this adder accelerator that we have, and we also have an FFT accelerator that integrates work from UC Berkeley on building nice, fast, efficient FFTs. And future work for this kind of stuff. So obviously, like this notion of emitting extra XML, you could also think about emitting test benches, emitting Linux drivers, trying to make it just dead simple for people to go and write hardware. But also, if they don't want to use the System C HLS, high-level synthesis kind of approach, they can do this but still get the benefits of all the collateral that automatically gets generated. All right, so this is just links to the project, some stuff about me. So the main project is this ESP project. There's the Chisel accelerators, which is a submodule of that. For Chisel 3, that's on Free Chips project, but that will eventually switch to another project called Chips Alliance. We have a Chisel 3 Twitter. There's the FIRRTL project and my GitHub, if that's of any interest. And that's it. And I think I somehow got back on time after that interesting start. So thank you. Sure. Any questions? Shoot.
Is there like compiler of Chisel to C or something to simulate it?
So we try and just take advantage of open source tools. So FIRRTL is like an open source compiler of a Verilog file to a C++ executable that you just build with GCC. So that's like the how do you get it to C++ to simulate it. So we just use FIRRTL for all of this stuff. But there does exist another project called FIRRTL, which lets you just directly simulate the FIRRTL IR, and you can use that for testing too. So we have all a bunch of unit tests with this thing. You just type spt test, and it runs all the tests for the accelerator as it goes along.
Can you go from System C to
I'm actually not sorry, I need to repeat the question. So the question was, can you go from System C to FIRRTL? I'm not aware of that right now, but the project Yosis does have a Verilog frontend and a FIRRTL backend. So you can theoretically try and take advantage of like the FIRRTL compiler ecosystem from Verilog. So, you could go System C to Verilog to FIRRTL if you wanted to, but you would probably lose a lot of semantic information along the way. Sure. Yeah, so the question is, what are the benefits of Chisel versus something like System C or Verilog? So generally, the way that I understand you're going to use System C is sort of if you have these macros, and you're very restricted in the set of what you can do. With the benefits of Chisel, it's basically saying, you get all of the last, 40 years of software engineering, and you can really apply whatever programming paradigm you want to the process of hardware generation. So you have first-class functions, you have parametric polymorphism. There are no restrictions in the sense of you don't have a synthesizable subset. It's just whatever you want to use to describe hardware, how it connects, and you can build more complicated libraries on top of this for doing whatever you may need or your company may need. So,
yeah, we got a minute.
Got a minute. Anything else? Do you want to borrow the minute? I can yield time too. So I'll be around if anybody wants to talk about Chisel or any of this kind of stuff today and tomorrow. So thanks, guys.